Actually, the opportunity to speak. Just to clarify on the organizational side, should I expect questions as we progress, or should I try to answer them at the end? I'm open if we want to have it like a little bit of a discussion. And if someone feels urgently needs to ask a question, I'm more than happy to answer halfway through.
Yes, Edward. Typically, we will ask questions if anything not immediately clear from your presentation. More substantial questions will be asked at the end. But if anyone wants to ask question, please send me your note in the chat, and I will moderate it.
Right. Okay. So I will present today a talk about the solar flare energetics and the role of X-ray, or probably more specifically hard X-ray diagnostics for the purposes of improvement of understanding of solar flare energetics. This probably is well-timed presentation, since just 1 month ago we had a RESI workshop in Dublin, where quite a few interesting presentations were on the topics related to X-ray diagnostics of flares. This is the work done in collaboration with a few people from Glasgow as well as America. And let me start with something that probably you definitely heard of or are partially aware. So I would like to attract your attention to the object that I'm going to speak about, the solar flares, and probably this will repeat the thoughts of many who study this. Why we are interested about flares and in general coronal mass ejections, because of the not only that they are complicated physical objects, but also extremely energetic, and as a result of it they demonstrate quite tremendous display across the heliosphere. And it might be a good start to think about a little bit about the numbers. That would be the main motivation in this talk. So I copy and paste the work that was done by a group of people, large group of people, actually more than one group of people, who looked at the energetics of solar flares. And specifically, they try to do energy partitioning between the key ingredients of solar flares, specifically hot plasma, non-thermal particles, magnetic field, kinetic energy, energy of the ions, as well as the kinetic energy of ejected plasma that is related to a CME. And typically, and it's quite interesting, they find that the numbers for non-thermal particles, for energetic particles, or the CME energy, and as well as the thermal plasma, they are roughly, for a large flare, in the order of 10 to the 31. So depending on which one is larger, it probably will be changing the way how we interpret this. So from this perspective, the key here is not only the knowledge of the order of magnitude estimate, but also the precise knowledge of this energy. So for example, if this energy is a factor of 10 larger, it might change the way how we look at the flares in comparison with others. And we might need to look at different models or put more weight at the other processes. The important thing that comes from these papers that put these numbers together and catalog quite a number of events. There is a follow-up paper by a few other people, including Emsley and Swandon, 2016, is there is the order of magnitude uncertainties normally put on the non-thermal electrons within a flare. So why this is important? I will put or try to put these numbers because of the limited time in the context of a standard solar flare model, where we have magnetic energy that is converted into fluctuating electric and magnetic field in general that leads to acceleration or probably heating, which is still unknown. And then these electrons, energetic electrons and ions appear in large numbers, and they are propagating along the field lines, or if there is escape into point to escape. And finally, they collisionally lose their energy, and we see these foot points through bright hard X-ray emission. Also, the large energy deposition to chromospheric layers unavoidably leads to radiation, and strong emission in H-alpha, for example, was for a long time considered to be the main diagnostic of flares. Nowadays, of course, we look probably mostly in X-rays, thanks to the spacecrafts that are orbiting the Earth as the main feature of the flare. So now flare and gauge X-ray increase is synonym nowadays. So why X-rays? X-rays are extremely attractive for the diagnostics of energetic particles because of this relatively simple relation. And it's been realized early that if we know the probability of the emission or emission cross-section, then the observed X-ray flux is simply proportional to the unknown electron distribution or electron flux weighted by the density. So if we know observed X-rays or spectrum of observed X-rays, we can go and determine the electron distribution because these values are normally well known or known to a sufficient degree of accuracy to facilitate this relation. The main processes that are contributing to observed X-rays, and this is a typical X-ray spectrum, going from lowest, what we have here, around 10 keV and to a few hundred keV, would be basically Bremsstrahlung over this range. Mostly, well, or it's free, and mostly it is electron-ion Bremsstrahlung. At higher energies, starting from around 300 keV, electron-electron Bremsstrahlung starts to be important, and in this range below 10 keV, free-bound emission contributes substantially to the observed spectrum of X-rays. I see Alexander Lysenko raised hand. I don't know, am I supposed to act somehow on this? Hello, Gregory?
I don't see anything. Sasha, do you have a question?
Because it's appeared brightly on my screen. So.
No, likely not. Yes, just go ahead.
Okay.
She had some technical problems, so just go ahead.
Right. Okay. And let us speak a little bit about the parameters that what we infer, so, or the main features of the spectrum that this has been known for a while. So first of all, this is the thermal part of the spectrum, normally imaged in the loop top regions of flaring, of flare. This part, it looks like, or well approximated as a power law, and normally associated with these foot points shown in blue. So this part normally comes from the corona, and this one comes from the foot point. Why it is so? It's again, one can probably expect this from this proportionality coefficient. The higher the density, the more efficient particles will be collisionally stopped. So from this perspective, this part kind of would be expected to come from denser regions of the atmosphere. Sometimes we see also thermal emission in the intermediate range, close to the emitted region. Also, it's quite interesting is that for the majority of flares, to a good approximation, we can say that the spectrum is a power law, as shown here, with a spectral index in photon space around, on average, 3, but it could vary either way. So, as I already mentioned, in the coronal region, we have normally temperatures between 1 and 3 10 to the 7 Kelvin. So if you prefer, it would be between roughly 1 and 2.5 keV. And in the region associated with the food points, we don't see such bright emission, but sometimes probably at the top of this region we can see soft ray emission. And the bulk of this hard X-ray emission comes from this very well localized regions in the atmosphere associated with the food points. And with RESI we can well resolve this. So because of the wealth of this spectral information, it is important and has been used already this knowledge, or the knowledge of the spectrum, to determine the properties of the energetic electrons that are responsible for this non-thermal part of the particles. So how is it done normally?
Edward, at that figure you also had green and black dash, ellipse, and circle. What they are?
It kind of goes beyond the purpose of this presentation, but green is northern food point, black is southern food point. So the this line is the spatially integrated spectrum, and these two lines are spatially resolved spectrum. So green from the southern food point, and green from northern, and black from southern food point.
Okay, thank you.
The bulk of emission comes from the southern. This is the same flare. You see, this is brighter than this at particular moment when the image was taken, and when the images were taken.
Okay.
Right. The main way how we estimate the energy and how the large group of people came to the numbers about the role of the energetic particles comes from relatively old paradigm of estimating the energetics. So first, people use extensive the expressions that I just showed, that the photon flux at the Earth is simply proportional to the so-called mean electron flux spectrum that is basically within flare region, and it's weighted by the cross-section. This value is known, and normally it is done assuming isotropy of the emission. There are some reasons to believe that it is not far from the truth, but it's probably a separate story. So we have isotropic distribution of particles that also will depend only on energy, so it's just an integral. And one can relate this value to what you need to inject into the dense atmosphere in order to provide this mean electron flux spectrum. If you know how the particles evolve in energy space, and if you assume, for example, thick target, normally it is collisional thick target model, then this value is giving us immediately the accelerated or injected spectrum of the electrons. And as you see here, there is no free parameters. The density disappears because of the integration, and this value is giving us the relation between the absorbed flux and the injected or accelerated electron spectrum. We already saw that this part, because of the behavior of the cross-section, should be also roughly like a power law, similar to what we observe. So if we know the injected spectrum or we know the spectral shape, one can use this assumption to determine what has been accelerated in the particles. The main problem here arises, well, probably two parts. One is probably not that crucial, is we normally, just because of the finite area of our instruments, we do not know what is happening often. We don't know unless it is very strong flare at high energies. Normally background in photon space covers the spectra and it's not visible. So as a result of it, the highest energy part is not always well observed, as I said, apart from the cases when we have very strong flare, and it's normally X-class flare, but for small flares, it's normally hidden by the background. And the other problem that is more severe is related to the probably well-known low energy cutoff problem. And this is one of the main things that is affecting our knowledge of the energetic. Why? Simply because it's a power law, and for a spectral index something that I already said, 3 or 4, when you do the integration, the integral or the area under this curve is given or chiefly determined by the lower energy cutoff. So if you have an error in this value, say by a factor of 2, because of this power, 2 to the power of 4, it's 16, so you've got almost 1 and a bit order of magnitude uncertainty. So just a small uncertainty in this value brings very large uncertainty into the injected spectrum and hence the energetics. And as already mentioned, this strongly might affect our interpretation of flares. For example, one of the recent papers suggested that this energy might be too large to have sufficient energy in the magnetic field to accelerate. So this part of the talk, or the next part of the talk, will be devoted what we can do in terms of the best practices to determine this injected spectrum and hence determine the energetics and probably eventually determine how we can better understand the energy partition in flares. So this is the picture taken from a paper by Jack Ireland that is basically showing the very same thing but using Monte Carlo simulations. For a famous 23rd of July flare, they calculated the uncertainties on lower energy cutoff using a standard collisional sig target model and using more than one Bayesian, Monte Carlo, chi-square mapping, covariance matrix approaches, estimated the uncertainties. What you can see here, well, first of all, is that the uncertainties are huge. It's not only a factor of 2, it's a factor of 10. In other words, what it means that if you take these values with such uncertainties, it means that the energy that you are concerned about are probably indeed underdetermined within a factor of 10. And if it is so, it's very difficult to check existing models with respect to such uncertainty on this key parameter. One particular way they use is they use full chi-square, so it's not normalized by the degrees of freedom. It's a full chi-square, and what we can see is that this full chi-square is basically flat and small, and at the level of, I think it's 2 sigma, you can take any value between 40 something all the way to lowest energy. So obviously it's not satisfactory, and over the last 2 years, we were looking at this problem and trying to address this issue. And we are basically considering the physical situation or adding the physics that must, we believe, present in flares in order to constrain this lower energy cutoff and hence better to determine the energetics of the flares. So first, one bright and important thing that we observe in flares is the existence of hot material. So this hot material exists all the way from the food points to the acceleration region, and sometimes we see a beautiful hot loops. This is in RESI, so the temperature here is around 2 kT or even higher, and the electrons must be propagating within this hot plasma. So from this perspective, immediate difference between what you would consider more natural is the propagation in hot plasma in comparison to what you would do in the coronal plasma. So what does it make in terms of the picture difference? In terms of picture difference, there is two main aspects that needs to be highlighted. First, it's the way how the energy is changed by the particles. In the cold plasma, the higher the energy of the injected particles, the further they will propagate in plasma, and they will propagate until the energy will turn into zero, or collisional column depth is such that it's basically compensated for the initial energy. So the higher the energy, the further down these particles will propagate. If we consider more realistic approach, when we have warm target, this behavior becomes much more complicated. So first of all, for highest energies and for purpose of being more practical, say above 40 or 50 kV, they will propagate in exactly the same way. But the interesting thing starts in the energy range, which is relevant to the cutoff energy. It's roughly 20 or around energy. So in this case, the particle will propagate and will start to lose energy, but it will never will have energy less than the thermal energy of the plasma. And this particle will, after they thermalize, will diffuse, and they can end up in the corona, in the chromospheric region, if there is a density gradient or continuous injection of this particle. The same applies for very low energy particles, so they also will continue and will diffuse through this region in both energy and space. So the main differences here appears is two ways. So the way how the particles are propagating and the way how they evolve in energy space. So here, all these particles, as soon as they stop, they're basically removed from the system. And here, they are never removed because they are still in the range that might be visible by RESI. And they are only removed if they thermalize to the energy which is invisible by X-ray spacecraft. So this is the basic idea, what we call warm target model. Of course, warm target model is a bit of a simplification, so it includes region of hot and essentially region of cold plasma, and it also includes not only the modified energy evolution, but also diffusive transport of the particles. So how does it look in simulations? Well, that's the work by Natasha when she was a PhD student here in Glasgow. So she did these simulations, and what we can see is probably similar to what we saw in pictures. So if we inject particles, in both cases the same particles were injected. The difference is that this is a low density corona and this is high density corona. So in the case of very low density, something like 10 to the 10, the bulk of the particles above 10 kV propagate and into the dense chromosphere and produce very bright food point. In case of higher density, something like 10 to the 11, you see the bulk is visible here. The important aspect here is that what is the spatially integrated spectrum, or what we will see in X-rays. In the case of very low density or very low temperature, you will see that the results are actually not far off from a standard, the blue line, collisional thick target model with a cutoff at 10, while in this case, there is a substantial contribution from these thermalized electrons that are still propagating in this region and didn't reach the cold chromosphere. And this part, this is RESI spectral part, is well visible and in the hard X-ray spectra. And what we basically started to do is to use this part as well as this part as a constraint for the injected particle. So if you want me to say the very same in terms of the equations, so the difference is that we have not only collisional drag modified by the finite temperature, but also have collisional diffusion, and what's importantly, we have collisional scattering that facilitate the diffusive transport of the particles inside the hot coronal part of the plasma. And this is the main difference. Importantly, that this equation doesn't have a stationary solution unless you provide the boundary where this particle will escape. The reason for it, or can be seen relatively simple. This part is the injection, and this collisional operator, this and this together, they conserve the number of particles. So strictly speaking, the solutions that would be stationary in this equation does not exist. It only exists if you have warm and cold target as you have in a real flare situation. So in other words, this T will have two values, one very small for the corona and the other which is large, and then this value will have stationary solution. So as soon as we are happy with the equation, we can relate the mean electron flux, the one that I already introduced and served as a fingerprint of accelerated particles, with what is accelerated. This relation becomes different from what we had in a standard collisional target. You see the appearance of temperature, so, and also the appearance of the characteristic scale where the hot plasma exists. So there are three new parameters: the length of the loop where this hot plasma exists, the temperature of the loop, and the density of the loop that is appearing. And if there is a balance between the particles that are diffusively escaped and thermalized, this would provide us additional constraint. So how does it work in practice? This is a different minimum energy that is determined through the basically thermalization time. And we see that if we change this energy, or in other words, change either temperature or the density, this part starts to grow. And eventually, it will hit what we see, or what we see as observations, and we cannot move further. So basically, this tells us in pictures how we can constrain the lower energy cutoff. So if you inject more lower energy electrons, they will be visible through the thermalized part of the distribution. Right. Now let us go to real data and take a look at the RESI observations and how RESI observation can tell us whether we have improvement here. So this is a typical flare where we use this warm target fit and the thermal fit, the combination of these two. And we draw a similar picture inspired by Ireland. So this is the blue delta chi-square, full chi-square, not divided by the degrees of freedom. And I show 1 sigma, 2 sigma, and 3 sigma, or if you prefer 99%, 95%, and 68% confidence level. So what we see in blue, which is a cold target, is that here you indeed cannot move far at 3 sigma level, but with 99% confidence, you can say that the lower energy cutoff could be anywhere between this, what all specs would return as a minimum, from this value all the way to the lowest energy. So it's again over 2 orders of magnitude freedom in terms of choosing how much or what is the energy that is going into the flares. It's quite important that for the warm target, you don't have such freedom. And with the if you take again 99% confidence as a level, this uncertainty is around, I think, 3 kV. So between here and here, 4 kV. So within 4 kVs, we can determine it at 99% level, and there is no way we can move or take lower values of the low energy cutoff. For each value of low energy cutoff, it's quite easy to calculate the power in these electrons, and one can see that if you change it as would this model predict, you can easily get it by 2 orders of magnitude for these values and probably continue this way. For the warm target, there is a well-defined range over which you can say either with 1 sigma or 3 sigma uncertainties. 1 sigma is the uncertainty that normally you would get from standard software or specs that is producing this characteristic curve in chi-square. So what else needs to be emphasized here? The other important aspect is the fact that now our model depends on the characteristic scales and the characteristic temperature and characteristic density of the flare. So if you change the length of the loop, for example, you have very bad imaging, you change also the power of the electrons through this equation. So if the length is larger, you have immediately lower energy, and the warm target fit will provide you uncertainties if you choose particular range. The same applies if you start to play around with the number density of the particles within the loop. So if you assume different densities, it will change the values. And each similar argument applies for the temperature. So this was done for various uncertainties of the value, and you can see.
Edward, let me clarify. The temperature and density are parameters you select by hand. They are not determined self-consistently from the solution. Yes.
No, they are not determined by the.
Or from observation, not.
You're from the observations,
yeah,
but not from the model. Yeah.
Okay, thanks.
Yeah, and basically changing these parameters, for example, if you don't, if you know, gives you an opportunity to determine this very accurately. So I already, I think, approached, yeah, it's almost 40 minutes I was speaking. So it's my last slide, where I would like to emphasize for those who is interested to put a hand on this and try the resist warm target model. Added to all specs, the important conclusion comes is that this finite temperature plasma effects play a crucial role when we want to determine the energetic of solar flares. And if you assume either thermal temperature, you determine lower energy cutoff within amazingly 14% uncertainty. And it's at 99% level, I think. That gives you not only the number, total number of electrons accelerated, but the total injected power. And this was not basically available with the cold target approach, and such estimates obviously open us possibility to study partitioning, or how different energies compare within flares, within uncertainties, or in other words, to study these processes quantitatively, as opposed to have estimates. And I think that's all what I can say. So thank you.
Okay, thank you. Thank you, Edward. We are open to discussion and questions. Dale?
I have a question. Yeah. So, Edward, this is a really nice model that links the power law distribution of electrons that are injected to the thermal part of the flare. But this also assumes that all of the thermal emission is coming originally from a power law injection. In other words, there's no thermal energy released by the reconnection itself. Can you talk about how valid that is and what you're...
the model, of course, considers the problem. Here is the electrons, which are accelerated and injected in hot and cold chromosphere. But it does not exclude a modeler. Like if you believe that there is a certain amount of energy goes into direct heating, you can always add on top the thermal component. So this is open to modeler, and if within your model you must have fixed thermal component particular, you can obviously add it on top.
But without much of a constraint observationally, I guess. It's sort of ad hoc in that case.
Yeah. Well, of course, yeah.
I think this is related to my question about how you determine temperature and density in the inversion, in the fitting, in the warm function. I think that given that in practice these values are determined from observations, I think implies that all sources of heating are taken into account, and then the model tests how much power law contribution would or could change it if it extends to lower and lower Emin. And from this you get eventually your constraints. Or I'm awfully wrong. That's
one of the ways how to view it. So if you, for example, believe that there is a particular plasma that must be formed by over a certain period, and you study the next temporal or next moment or next range in time, you can say that there ought to be plasma that is measured, thermal plasma, and you take the temperature and the density from this one time interval before, and then you study what is happening if you inject on top particles which must be propagating and diffusing quickly. So you can answer it by splitting into pre-existing, it's to a certain extent similar to what Gregory said, to pre-existing and then add it on top plasma.
Dale, is it satisfactory?
I guess so, although I wonder how, because I thought what was happening is we were getting a self-consistency between the observed thermal distribution and the non-thermal power law distribution.
That's correct. There is a self-consistency in the model. Yes, that's right.
Yeah.
But you're saying that a thermal component can come from other than the injected component and still be self-consistent.
Well, if you split it in time. Now, Dale, I think in your question there is a confusion of two things. It's self-consistent over a finite period of time. So this equilibration happens on the time scale probably around 10 or 20 seconds. This collisional times, or collisional diffusion time, right? So, but you might want to analyze flare that evolves for tens of minutes. and consider what will happen, or if you have hot plasma already, you see in some instrument at the beginning of the acceleration phase. Then you need to take this pre-existing plasma and on top of that add the plasma that is self-consistently appearing from non-thermal particles.
Okay.
Does it make sense to you that there are two things, that it's self-consistent solution for a given moment of time, but it doesn't tell you how the flare evolves in time. You need to put some observations.
Mm-hmm. Okay, thank you, Edward. Other questions or comments? So, someone wanted to unmute microphone a few moments ago.
Well, that was me, Hugh.
Hugh, go ahead. Yeah.
Okay, so Edward, this is very nice, and I think these model concepts relate very well to what we traditionally have called the monolithic flare loop model, where there is a single structure. But a more modern view of flares is that there's a lot of filamentary structure, fibers, and very small spatial scales, limited by resolution of instruments, much better than RESI, and very short time scales implied by those spatial scales. So would you like to comment about the way in which this kind of multi-filament fiber description of a flare could be accommodated? And I'd like to just comment that Jeff Reeb is pointing, and Jim Klimchuk, people like that, are pointing out that you may have tens of thousands of fibers that are operating independently.
It does not exclude at all, and this model is easily applicable to tens of thousands of fibers. There is this, as we discussed with Dale and Gregory, there are parameters that would characterize these fibers: length, temperature, and density. So if you've got substantial variation between different fibers, you need to consider this model for individual fibers and then sum it up. And why you just simply sum it up? Because it's basically incoherent addition of X-ray emission from individual fibers. So I think it's readily applicable to such scenarios. Indeed, there are observations suggesting that probably density systematically lower if you go up and higher if you go down within the flux tube. So that's pretty much consistent. So you just change the density for different fibers, you calculate and you sum up and you got the result. So I think it's good to be tested. Hugh?
Hugh?
Yeah, that's fine. I guess what I worry about those two first is that the initial fibers may be very low density because the hot source has not had time to evolve yet.
Well, is there too low density, you would not see them. What we see is the emission measure, it's the density square.
Yeah, that's correct. You don't see them. I'm saying the emission, the hot source has not had time to develop, and so it is invisible.
Well, but we see thermal components, so it's not. It's basically we see this part of the spectrum, and it's always present. So it's not from square.
It's a question of angular resolution in the imaging, right? I'm saying that you cannot resolve these structures in soft X-rays, but you can resolve them in foot-point emissions like in the EUV, and they're very small, and they presumably are happening in flux tubes that are empty initially. So the particle acceleration is taking place in a place where there is no hot plasma yet present.
Well, if it is a more philosophical statement, I would say probably it's very difficult to facilitate because, well, you need some particles initially to accelerate.
Oh, Edward, I believe that the question of initiation of flare, which can be initiated in really very tenuous flux tubes, and I could add that in this case, when it's invisible for hard X-ray, it would be visible for microwaves from corona. So other questions? Edward, let me ask you, in the perspective of flare energy partition. So you presented like algorithmic way how you can improve this treatment of energetics and in particular of non-thermal component. But I wonder, could you comment about studying same thing by special selection of events, like selection of events which demonstrate extremely low thermal component, such as low energy part of non-thermal component could be studied in more detail with more confidence. Which we call sometimes cold flares, but they're not necessarily cold, but still showing very low thermal component.
Yeah, that's basically from this perspective. I would say, well, what you see here is the dependence on this E means that in its own turn is a function of the length, density, and temperature. So if we have roughly the same temperature along these flares, this drop or change in this is interpreted in terms of the very, very low density plasma. So obviously, eventually, if you have very low density plasma, all electrons will weakly interact in the corona and will go into the cold chromospheric region. So we can even put numbers. I think it needs to be below roughly 5×10⁹. So if you've got density more than 5×10⁹, it's pretty much guaranteed that you will have strong thermal component as a result of non-thermal parts or non-thermal particles. And for the case of very low density, and I think it's a number, if I'm not mistaken, around 5 or 3×10⁹, the result or the main effect will be here, where we normally don't see in Resi and in GOES as well. So from this perspective, yeah, it provides interpretation in terms of the low density.
Okay, thank you. More questions? I'm just looking for microphones, and it seems that all microphones are muted. So, Edward, this implies that we conclude your presentation. Thank you very much, and thank you very much for all the participants for taking part. And next event will be in 4 weeks. The speaker is Martin Lamming, who will be talking about first ionization potential effect. So thank you very much. See you in 4 weeks.
Thank you.
Thank you. Goodbye.
Thank you.